Good day, everyone. Today we are talking about section 10.2, operations with radical expressions. So our targets for today, I can simplify radical expressions, I can add, subtract, and multiply radical expressions, I can rationalize the denominator. So building off what we did in section 1, where we broke down radicals, our next step is talking about adding and subtracting, and then we'll get into multiplying as well. In order to add and subtract radicals, they must have a like radicand. The radicand is the value under the square root. So we have a square root symbol here. The value that's inside, whatever this is, that's called the radicand. So whatever's inside, whether it's just an integer, it's an expression, whatever it's called, whatever's inside is called the radicand. And so when we look at something like this, we have, this is a 4 root 10, and this is negative 9 root 10. Those are like radicands. 13 is not. So if we go back back in like chapter 1, and you think about what you did in like probably 6th grade or 7th grade, and you talked about collecting like terms, well, when we're dealing with radicals, in order to be like terms, they have to have the same radicand, the same square root. And again, when I add these, 4 root 10 plus, because we always add like terms, so 4 root 10 plus negative 9, you're just adding those outside coefficients. Negative 5 root 10. Again, the inside value does not change. And then we have plus root 13. When we are listing radicands, we have multiple radicals. We go from smallest radicand to largest. So root 10 is smaller than root 13, so that is why root 10 goes first. When we look at the second expression, we go, oh, root 2, root 18, there's nothing in common. But before I can say I have my final answer, I always need to ask myself, does the radical break down further? Does root 2 break down? No, but does root 18 break down? Yes. So root 18 becomes root 9 times root 2. Root 9 we know is 3 root 2, and this negative tracks down with it. I personally rewrite the problem so it's all on the same level, so I'm going to bring this 2 root 2 down. So I have 2 root 2 minus 3 root 2, and now is where I would say, okay, I have like radicands, so I can subtract, and I get negative root 2. If I want to put the 1 in there, I can put the 1 in there, but I do not have to. Personal preference on that one. All right. So for the rest of these, again, if it breaks down, like root 48 breaks down, you need to break it down before. This one with 3 is just like the one above. With 4, you need to break down, like 11 doesn't, 3 doesn't, but 27 and 44 do. Break them down. Add like terms. Again, the smallest radicand goes first, and then you go build up. So please pause the video and try each of these on your own. All right, so we start with the top one here. Root 48 breaks down to be 4 root 3. 5 root 3 and 4 root 3, we have a common radicand. We add those outside coefficients to get 9 root 3. The bottom left here, again, the root 5s, they're the smaller radicands, so we go to collect those first. So 7 and 4 would add those to be 11 root 5s. There's nothing going on here with this negative root 11, so it's just negative root 11. So 11 root 5 minus root 11. On this last one, 3 root 11 doesn't break down. Negative 2 root 3 doesn't break down. Root 27 breaks down. Root 9 times root 3. Again, remember to multiply this outside number. So if you want to bring it down and go it's 4 times and put that multiplication symbol in front, by all means. 4 times 3, 12 root 3, 5 root 44. Again, root 44 breaks down. 4 is our perfect square. that 2 from the square root of 4 gets multiplied by that positive 5 out front. That's why it's 10 root 11. Again, when I'm collecting like terms, I'm starting with what is my smallest radicand, in this case 3. So I have a negative 2 root 3 and a 12 root 3. I add those together to get 10 root 3. I have a 3 root 11 and a 10 root 11. I add those to get 13 root 11. So that is adding and subtracting. Basically, it's like collecting like terms. Multiply radical expressions. Again, outside by outside, inside by inside. So numbers that are outside of a radical multiply by other outside numbers. Inside numbers multiply by other inside numbers. If there's one term on the outside, we're distributing. So the rainbow thing. And so when I go 6 times root 5, well, 6 is outside, the 5 is inside, so it's just 6 root 5. If I want to think about it, there's a 1 in front of that root 5, so the 6 and 1 multiply. Here we have 6 and 2, we multiply those together and we get 12. Now, the last thing about this, when we write answers, we talked about how we write from smallest radicand to largest. Numbers without radicands, aka integers, go in front of anything with a radical. So the radicals are always at the end. So our final answer here would be 12 plus 6 root 5. Yes, the order is important, so make sure you are putting those integers first. Let's walk through another one here. So this time we have root 3 that we're distributing. So root 3 times 4. Again, 4 is an outside number. There's no radical there. 3 is inside, so when they multiply an outside and inside, they take their respective places. 4 outside, root 3 inside. Here, when I have root 3 times negative root 12, well, this is negative because positive times negative. Again, if I want to think about it, there's a 1 in front of each of those radicals. We just don't write it. So 1 times negative 1 would be negative 1. Root 3 times root 12, root 3 times root 12 would be root 36. Again, when I'm dealing with radicals, I have to ask, does it break down? Does root 3 break down? No. Does root 36 break down? Yes. That's 6. Negative 1 times 6 becomes negative 6. Well, that's an integer, so it goes out front, plus the 4 root 3. Again, integers in front, radicals in the back, from smallest to largest radicand. If you think you got it, go ahead and try this next one on your own, but I'm going to walk you through this one just for one more example. All right, so root 5 times 4 root 10. Again, if you want to put a 1 there to have an outside number, so you're going to multiply the outside. So 1 and 4 get multiplied. Root 5 and root 10 would make root 50. Again, when I do the second one, 1 times negative 1 is negative 1. Root 5 times root 20 is root 100. Whenever I deal with radicals, I have to ask, do they break down? Root 50 is root 25 times root 2. So this becomes 5 times 4 root 2. I'm going to hold off on writing my final answer because I'm going to wait and see what happens when I break down root 100 first. Well, I know this is actually 10, so negative 1 times 10 is an integer, and that number will go first. So negative 10 plus, and now I'm going to circle back to this root 2 number. So it's something root 2. 4 times 5 would be 20. All right, you're not going to see too many with having outside and inside numbers, but it is possible. When you have two binomials, this is like what we did in chapter 6 for multiplying. This is where you can use area, split, stack, although you're going to find that stack isn't the greatest at this moment. Like stack can be a bit of an issue, but you can work through it. As long as you know how to do stack properly, you can do it correctly. And then of course FOIL. I'm going to show you the area method on this first example. So again, the operation goes with the second term. So 4 and then negative root 2, 7, and positive root 2. And again, when we do the multiplying, just like before, 7 times 4 is 28. 7 times, if you want to put a 1 in there, so you get negative 7 root 2. Here you have 4 times positive. Again, you want to put a 1 in there, you can. This is positive 4 root 2. Negative 1 root 2 times positive 1 root 2, you get negative 1 root 4. Now, before I collect like terms, I have to go through any radicals and go, do they break down? Does root 2 break down? No. Does root 2 break down? No. Does root 4? Yes. That becomes 2. Negative 1 times 2 equals negative 2. Now, I go to collect my like terms. I start with integers. Well, I have an integer here, and I have an integer there. So 28 minus 2, 26. And then I have these like terms. They're both root 2, so they have a like radicand. So just like earlier, we're going to add the coefficients. Negative 7 plus 4 would be negative 3 root 2. The last one's not too much trickier. Yeah, there's a couple more radicals. If you want to pause the video and try it on your own, by all means. But I will walk through this one as well. And again, I'm going to stick with using the area method. I find that most people have success with this method, so I'm going to stick with it. So again, the operation, I chose to put the root 7 plus root 2 on the side. You could put it on top. It doesn't matter. Root 7 times root 7, root 49. I know some of you are like, Mr. A, that's 7. Just bear with me. We'll get there. Again, if you want to put the 1s in front, you can. 1 root 7 times negative 3 root 2. So 1 times negative 3 is negative 3. Root 7 times root 2 would be root 14. 1 root 7 times 1 root 2. 1 times 1 is 1. Root 7 times root 2 is root 14. Again, I'm going to put a plus in front. Negative 3 times 1 is negative 3. Root 2 times root 2 is 4. Again, root 4 we know is 2. Negative 3 times 2 is negative 6. So I'm going to go ahead and do that right away. We knew that root 49 was 7, so I'm going to cross that out and make it 7. Does root 14 break down? No, so I don't have to break down the root 14s. All right, start with the integers. 7 and negative 6, I add those, I get 1. Negative 3 and 1, I add those together to get negative 2 root 14 is my answer for that. We will do a bunch of these. We'll start with distributing, and we'll do a bunch of these binomial ones in class. I know they're tricky. They take practice. All right, the last thing we're going to do is we're going to look back at fractions again, because we need to talk about rationalizing the denominator. You cannot leave a radical in the denominator. So the process of getting rid of that radical is called rationalizing. And so what happens is, to rationalize, we multiply by the radical over itself. All right, and I'll explain that here in just a little bit. So we start here, we have root 2 over root 9. We cannot leave a radical in the denominator, so first thing we ask, does root 9 simplify? Does it break down? And yes, root 9 is actually just 3. So because it's a perfect square, we don't have to rationalize or do anything. We just have to simplify, and we are done. All right. Next one, 9 over root 6. Does root 6 break down? No. Now we have to go through this process called rationalizing. And what we do is we multiply by whatever the radical is in the denominator over itself. Why do we do this? Well, what is any number divided by itself? So what is 3 divided by 3? 1. What is negative 8 divided by negative 8? 1. What is root 6 divided by root 6? 1. What happens when we multiply a number by 1? So 3 times 1 is 3. Negative 2 times 1, negative 2. The number stays the same. What we are doing is we are changing the numbers, the values that we are seeing, but we're not changing the value of the fraction. It's like changing 1/2 to be 3/6. It means the same thing, it just looks slightly different. And that's what we are doing when we are rationalizing. We're changing what it looks like, we're not changing the value. Up top, we have 9 times root 6. Well, 9's an outside number, 6 is an inside number. In the denominator, root 6 times root 6 is root 36, which we know the square root of 36 is 6. So our denominator becomes 6. You may want to make yourself a note here that any time you multiply a radical times itself, so root a times root a is just a. Root 6 times root 6, 6. Root 7 times root 7 is 7. Root 3g times root 3g, 3g. As long as the two radicals that you are multiplying are identical, whatever the radicand is what the answer will be. The last thing, we are dealing with fractions. So we have to check, does the fraction reduce? And again, we are talking outsides with outsides, insides with insides. So this 6 on top here, right there, is inside of the radical. There's no other radicals. So that one's out of the picture. There's nothing we can do with that one. We are looking at right here, this outside numbers. Does 9 and 6 reduce? And the answer is yes. They reduce by a factor of 3. So we can take 3 out of them and we get 3 root 6 over 2. That is our final answer. That is completely reduced. All right, we're going to walk through another one here. Root 3 over root 6. Again, we know that root 6 cannot break down. So we're going to multiply by root 6 over root 6. In this example, the 3 is inside. So when I'm doing this, I have root 3 times root 6. I get root 18. And I know my denominator is 6. Again, if I need to do this and go, that's root 36, by all means, you do what you need to. Now, we have a radical. Before we can say, yes, this is our final answer, we have to ask, does our radical break down? Does root 18 break down? And the answer is yes, so we have to break it down. Root 18, and I'm going to go up on this one, is root 9 times root 2, which we know the square root of 9 is 3. The root 2 stops, so we get 3 root 2 over 6. So the radical's been reduced. The next question we ask, does the fraction reduce? We have two numbers on the outside. Does 3 over 6 reduce? And it does. It becomes 1/2. You can write the 1, you don't have to. So root 2 over 2 would be our final answer. So always have to check, does the radical reduce further? Does my final fraction I have, does this reduce further? Those are two things that are commonly forgotten about. Let's see here. You should be able to do the next two blue ones and try the green one as well. So pause the video and try each of the three on your own. All right. So 6 over root 3, we multiplied by root 3 over root 3. You get 6 root 3 over 3. 6 over 3 reduces to be 2 root 3. That one's pretty straightforward. This bottom row, a little tricky here. So we have 3 over root 8. Some of you might have multiplied and said, oh, root 8 over root 8. I got 3 root 8 over 8. You're fine, but then you always have to come back to that question, does the radical reduce? And so what some people will say is always look, does the radical reduce first. So we have root 8 in the denominator. I'm going to break it down to be root 4 times root 2 to get 2 root 2. And that's why you see 2 root 2 right there. And then when I'm multiplying, I'm rationalizing, I'm only multiplying by the radical part, so the root 2. And that's why you see I did root 2 over root 2, and you get 3 root 2 over, and again, root 2 times root 2 is root 4, or just 2. 2 times 2 would be 4, so 3 root 2 over 2. The last one's kind of putting a couple things we've seen already together. So we multiplied by root 6 over root 6. We had root 18x over 6. We had to break root 18x down. You can see here root 9, root 2, and again root x didn't break down, so that stayed inside. So you get 3 root 2x all over 6, and then 3 over 6 reduces to be root 2x over 2. We're going to do a couple more of these. So here, again, the top two, straightforward. So I want you to pause the video and try those two on your own. All right, these two are easier than the last two we had on the previous slide. Here we multiply by root 2x over root 2x. You get 9 root 2x over 2x. Nothing to simplify, nothing to break down. Same with the one on the right. You multiply by root 3b over root 3b. 2 and the 3b are inside. You get root 6b. That doesn't break down. Root 3b, root 3b. Again, if you want to write it as root 9b squared, you can. You can just go straight to over 3b. Again, the b on the numerator is inside the radical. The b in the denominator is outside, so they cannot do anything. All right, root 9 over 75. This is going to bring up the point of simplify first when possible. So if you can simplify the fraction, sometimes you can simplify the work. So for example, 9 over 75 reduces to be 3 over 25. Again, if I can get the denominator to a perfect square, I want to do that because that eliminates some of my work. And then this becomes like last section where we just split it up. 25 is a perfect square, so we get root 3 over 5. That's our answer. This last one looks complicated, and some people are going to say, Mr. A, that's really hard. Break it down. Does 48 over 8 reduce? You bet it does. That reduces to be 6. X to the third over x to the fourth. Use our quotient property. We're left with x to the first in our denominator. That problem reduces to be 6 over x. So this becomes root 6 over root x. We rationalize it. So multiply by root x over itself. We get root 6x over x. The top x is in the numerator. That is inside. The x in the denominator is outside. There's nothing more we can do with this. Again, we will do a bunch of these in class. I know it's tricky. I know this video got a little long, but it's a big, important section. If you have questions, come to class ready to ask them. As we're going through this, make sure you're asking questions because this is a big, important topic here. Have a great day, everyone.